Okay, good afternoon. So let's try to finish regression today. So if you'll see what I've written on the side, we had the lecture 2 of introduction on regression. We talked about correlation. What is regression? We did simple linear regression. We talked about multiple linear regression. Then yesterday's lecture was mostly on solution. We looked at, for multiple linear regression, we looked at the closed form solution and we looked at the numerical solution. Today the focus will be regularization. What is it? And we'll see that. But before I go to regularization, I wanted to close these open loops, open threads from the previous lecture. So just show you what I mean. So in the simple linear regression, so this is the open loop is related to homework 2, which I asked you, applying the necessary condition, the sufficiency condition, the convexity, right? To tell whether you found the minima, whether it is a minimizer, it is not a minimizer, it's a global minimizer, so on and so forth. So I'm going to revise that once. The second thing from the open from the last lectures is the complexity of the numerical solution and the closed form solution, why one is cheaper, other one is expensive. And then we'll start regularization. So that's the goal. So to do that, I'm going to go to lecture 2, simple linear regression and the minima which you had found. So if you recall, in the simple linear regression, this was simple linear regression, we started, wrote the residue function, and then we said you have to minimize this residue function, so you're going to find the gradient of it. Gradient is differentiate with respect to alpha and beta, make it equal to 0. This everybody knows by now, right? And in homework 1 you did also this and figured this out, but this gave you the candidates for minimizer. I said you have to apply the sufficiency condition and you also have to check whether the minimizer is local or global. So this I had written here that we'll see in the multiple regression case. The necessary weight applied for sufficiency we'll see in the multiple, convexity also we'll see in the multiple. So now coming to the multiple case, by now which you know is that the data, input data is d-dimensional, output is still one-dimensional, you've got n points. So this was from the simple. Now coming to yesterday's part where we talked about multiple linear regression. So this was the closed form solution. And to get the closed form solution, we had written the residue function j theta is this, and then we had translated into a function of matrix vector products. This is what he had written. Then we had found its gradient and make it equal to 0. And then this I said, this part I had worked it out for you in the scribble, how to differentiate the second term, find the gradient of that. The first term I said it's worked out in homework 2. Also what is worked out in homework 2, the point which you get this is the candidate for minimizer because you have only applied the necessary condition. So you have to apply the sufficiency condition and check whether it is positive definite or not over the point which you have found in after applying the necessary condition, and then you also have to check whether it's positive definite over all of the space, which means that is the residue function convex or not, or global. So I'm going to just go through homework 2 once to emphasize this concept. Everybody with me? Okay. Please ask questions, Anna. So let's go back. Go back to homework. So this is the homework. Kuldeep's writing is good, so has worked out nicely. So I'm going to just go over these steps again. Is this readable to everybody? At the back, very back? Yeah? Okay. So this is the function which we derived yesterday. We had expanded it also yesterday and we had written it as in the form of 3 terms. The first term, the second term and the third term. And then the second term we had already worked out with on the board. The second term we had already worked out. That once you differentiate this 2 theta transpose x transpose y, you can see that you will end up getting just twice of x transpose y. This I had worked out, but the first term I had not. So the first term is worked out here. You can see the easiest way, of course in this case is initially we have written it in a general form. You've got the thetas, you've got the a's. I mean this x transpose x I'm referring to as another matrix A. And then I'm writing theta naught to theta d. So instead of working in a general sense, which may be difficult to prove, the we do it in a 2 cross 2 matrix. You can prove this generally also by using induction. So, but we are skipping this for the class. So assuming that you got theta naught, theta 1, 2 cross 2 matrix in this, you expand it, you'll end up with this. Then you take partials with respect to theta naught and theta 1, put them in a column vector format, solve it a little bit, and you end up getting twice of x transpose x. This is what we saw yesterday as the first term. Everybody with me? So you can go back and check. Now the question was how to find the Hessian of this. So this is the gradient. To get to the sufficiency condition, you had to find the equivalence of the second derivative, which is the Hessian. So now what you'll do, you'll take these terms here, which are these terms, this and this, differentiate with respect to theta naught, theta 1, put them in a row format, differentiate with respect to theta naught, theta 1, put that in a row format. That's what it's done here. J theta, theta naught. So this has become theta naught square, theta 1, theta naught, theta 2, and so on and so forth. I think ये 2 कहाँ से आ गया? theta 1 ही है, sorry, 1 है, it looks like 2. Theta naught, theta 1, theta naught, theta 1, and theta 1 square. है ना? So theta naught and theta 1 are there. Once you differentiate, you end up just getting the inside matrix, so you get twice x transpose x. Now the CS undergraduates have seen this in optimization. That's what I was telling them, that if this was what kind of optimization function is this? The CS undergrads? What would be the name you would give this? What class of optimization function is this? Sorry, I'm seeing some whispers, murmurs. Gaurav? I've forgotten all names except you. There's another Gaurav. 2 Gauravs I know. So, yes, Gaurav. Sorry? Well, unconstrained, yes, but in terms of linear, quadratic, cubic, quartic, what is it? Quadratic, right? So we've spent 1 or 2 lectures on this trying to tell this is a quadratic because of the theta transpose theta multiplication with the matrix here. There is a second degree term here. So you know that once you do the Hessian of this kind of a term, you will only get the middle matrix out. We have worked this out. Yes, Gaurav? Can you recall this now? Okay. So anyways, we have worked it out here. We first found the gradient, which is twice x transpose x theta. Then we did the Hessian and we get 2x transpose x. Similarly, for the second term, which we worked out yesterday, once you do the gradient of this, you'll just get 2x transpose y. When you take the Hessian of it, it will be 0 because there is no theta. The third term was without the theta, so the gradient of that was anyways equal to 0. So once you put it together, the gradient was this, which we had made equal to 0 and solved this yesterday. Everybody remember from the slide? And now we're looking at the Hessian. Now the question is this Hessian is independent of theta, which means that the point which you have found, theta is equal to x transpose x inverse x transpose y, the minimizer, whatever you will check for the positive definiteness of this Hessian, you don't have to check it at that point. It will be both the sufficiency condition and the convexity are together getting covered. Otherwise, sufficiency was checked at the point and convexity was checked for a general Hessian. Can everybody see? So here it's general. So now the question is, when is x transpose x positive definite? Did you guys read, those who are new to this, what is positive definite? You remember now? We went over this on Monday, right? So to show that when is this positive definite, how do you show? That you multiply with a non-zero vector on the left and a non-zero vector on the right, and you show that the scalar which comes out is positive, non-negative, or not even 0. If it is greater than equal to 0, then it becomes positive semi-definite. If it's strictly greater than 0, then it is positive definite. So that is what is worked out here if you look in the screen. So we say now x is positive definite if and only if for all non-zero u this term is greater than 0. So now what is this term? U transpose x transpose u. This can be written as xu transpose xu because when you do a transpose, this term comes in front. Yes or no? What is this? This is just A transpose A, or norm of A squared. The 2 norm of any vector can be written as any vector. 2 norm of a vector is A transpose A, the square of that, because the norm is square root. So you get rid of that. Now what's the definition of a norm? By default, norms are positive. They are non-negative, sorry. They are greater than equal to 0. So at least we were able to show that X transpose X is positive semi-definite. But for the sufficiency condition, what did we need? We need a strict positive definite. Remember, if X star gradient is equal to Hessian is positive definite, then X star is a strong local minimizer. We did this on Monday, the non-CSE people's undergrads, right? So when is this strictly positive definite? So we work it out, and that's the case if the columns of the X matrix are linearly independent. So if they are linearly independent, let's say this term is equal to 0, right? If you write XU is equal to 0, you will get U equal to 0 if the columns are linearly independent. This is the property of a linear set of linearly independent vectors, that you multiply with scalars and add them and make them equal to 0. All scalars are equal to 0, again coming from your linear algebra. So if your X has linearly independent columns, then it is positive definite. Then the sufficiency condition is satisfied. Correct? And now we showed that it is positive definite in this case, which means that it is convex as well, so it's a global minima. Although it's strictly convex now, because we made it strictly positive definite. In general, it is always positive semi-definite because it's a norm. So it's anyways a convex function. Any minima you find is a global minima. So let's say you apply the necessary condition, correct? And you get a candidate for minimizer. If your X, which is formed from this 0 and X matrix which we saw, has linearly independent columns, then this minimizer would candidate for minimizer will be a minimizer, and it will be a global minimizer. Let's say if the candidate for minimizer you get, and this X has linearly dependent columns. Let's say it is not linearly dependent, so you can't for guarantee say that it is a minimizer. You can't tell that, right? But whatever minimizer candidate for minimizer we found, it will definitely be global if it is a minimizer, because it doesn't require a strict convexity. It just requires a normal convexity. Is it making sense? Yes or no? So gradient equal to 0, you get a candidate for minimizer. Sufficiency is not always satisfied. It will be dependent on your problem, because X is formed from the problem vector. Remember, once the first element of the X, the second dimension of all the X, and the dth dimension of all the X. I'll show the X again. But whatever you find, if it is a minimizer, it will be global. Everybody okay? You go back and read this. If you have doubt, then ask me. Should I move forward? Doubt, then please raise hand. Like I said, if one person has doubt, there are multiple others who are confused. I can work it out on the side if this is confusing you. Everybody okay? I need an affirmative yes. Yes? Okay. All right. So this we completed one loop. Now let's do the second. This was our X. When I was saying linearly independent columns, which means that this, all of them are linearly independent, which means you take a linear combination of them, make it equal to 0, and the scalars which you'll use to add them up should all turn out to be 0. That's the definition of linear independence. In case you have forgotten, go back and remind linear algebra to you. Okay, we'll move forward. The second open loop from last lecture was the complexity. So what we did last time was we applied the closed form solution and we got this solution. Now I told you that this is a candidate for minimizer. If X turns out to have linearly independent column, it will definitely be a minimizer, but whatever minimizer you'll get will always be global. But the problem with the closed form solution was that there is an inverse of the matrix. It may not always exist, right? So there's another thought for you. If X has linearly independent column, will X transpose X be invertible or not? Think about it. Not for the class, but in general, those who are comfortable with this kind of argument. So then what we did, we said we're going to do a numerical solution because there is an inverse involved. To do the numerical solution, we said we're going to use gradient descent. Gradient descent says that you start from a point, find the derivative in one dimension or a gradient in the n dimension and add that to your initial iterate and keep iterating till the time you reach the minima. So this was the expression for that. So now you have to find the gradient of the Jacobian, which we found out yesterday with me. Sorry, this might be slightly small for you, but we did this yesterday. Hai na? So then eventually we got this term, that you had the gradient, the residue term, and then multiplied with xji. And then we showed that, for example, if you're iterating a gradient descent, how it's proceeding. So this you will do in the lab tomorrow. So the way I've designed this, there are 3 topics I'm covering, right, in the geometric models. One is regression, another is support vector machine, and the third is the distance-based model where we'll do clustering. For the lab, I've made a lab/tutorial, which means that you'll do the numerical, then you'll do a tutorial next, then you'll do a numerical, you'll do a tutorial. So they are in fact total of 8. So we'll see how we can finish all of it. But you'll practice both. You'll practice the code and you'll do by hand analytically solving it also. So tomorrow's lab is numerically playing with regression. So you'll play with the gradient descent tomorrow. And the following lab, you will practice more analytical problems on this. Is that okay? So where we had stopped last time was this, and the bottom part of the slide was not written. Is it readable? Make it bigger. Should I make it full screen or readable? Readable? Okay. So yesterday what I did was, I had not written this complexities here because there was less time and I wasn't sure whether you will get confused by reading this. So let's go over this today. So the very first thing what we had done yesterday, so we are still continuing the lecture 3 part. So we're talking about the complexities. Okay, so if you look at the X matrix, what was the X matrix? It was all ones, and then you were taking the first point, its first dimension, the nth point in its first dimension, all the way till the first point, its dth dimension, and the nth point, its dth dimension. Correct? In machine learning context, this x's are typically referred to as the feature vectors because these are the input to your problem. So that's the name which we use it, the features. So what is the dimension of x? So this is n cross d plus 1. They're n rows and they're d plus 1 column based on the dimension, correct? Now, what do we have to do? Remember, what was our theta? The theta which turned out was x transpose x inverse x times y. Correct? So, the very first thing you'll have to do is find x transpose x and then invert it. Now, when you're doing x transpose x, so what you're doing, you would take this matrix, you'll transpose this. So, this will be all ones here, and this will be, sorry, this will become 1 to x d1 and this will become x dn. Correct? This is d plus 1 rows and n column, and then you would have 1 1 x d1 and x dn. And this was n rows and d plus 1 columns, correct? Now the computer science people, is there anybody from math? Okay, okay, masters? Are you masters, PhD? Okay, so computer science and math people usually work with complexities, so it's not a problem. But those who are seeing it first time, how do you compute? What is the complexity of building this matrix? So when you say complexity, you refer to the primitive operations which you do to compute something. When you say primitive operations, I mean addition, subtraction, multiplication, division, something like that. I mean, you can say addition and subtraction are equivalent and multiplication. So you assume that the primitive operations take a certain amount of time and that is how you see how many of those you're doing, and that will tell you what's the complexity of this. So now if I have to find the product of this matrix, these two matrices, what will I do? I'll multiply this guy with this guy, and that will give me the first element of this. Correct? What is the, how many elements are you multiplying here? This and this. Sorry? How many elements are there in this row? N, and how many? Of course, there has to be the same number here because they are matching. So you're doing n multiplications, and you'll do n minus 1 additions or n additions. Something like you're doing operations to n. If you look at the primitive operations. Everybody with me? So the order of finding one element is n, which is linear. Correct? How many elements do we have in this matrix? So the cost of computing one element is order of n. You write in computer science order of n. You may have seen in your introductory programming also. Order means there is a constant in front. Just think of it that way. We don't write the constant because it doesn't matter. We are more worried about the powers of the n's here. So this is linear. How many elements do we have? Someone, one person, loudly. D plus 1 plus cross D plus 1, right? Or D square elements are there. If you ignore the 1, because D is typically much larger than 1, the number of elements here are D square. So the complexity of the whole thing is D square n. This is what I have written. The complexity of building this matrix, correct? Now what happens? Once you have built the matrix dimension is D plus 1 cross D plus 1, which is nearly D square. It's, the dimension is D if you want to just ignore the plus 1. So what's the complexity of inverting such a matrix? So the complexity of inverting a n-dimensional matrix is n cube, so a d-dimensional matrix is d cube. How would you find that? How do you find an inverse? You either apply Gaussian elimination, or you do LU factorization, or you find the cofactors and divide it by the determinant and so on and so forth. So this you can go back and see in your linear algebra. It's standard. The complexity of inverting an n-dimensional matrix is n cube. So the complexities for this task is n cube. Everybody agree? I'm sorry, it's order d cube plus order d square n, depending on whether n and d which is larger. I can't drop the d square n if n is million and d is 100, let's say. I don't know. But if d becomes 100,000 and n is also 200,000, approximately the same, then this cost will dominate. Yes or no? Everybody with me? Okay. Now let's look at the other side. Let's look at what's the cost of computing the solution numerically. Okay. So this was the closed form. Now let's go back and look at it numerically. Okay. To find the cost numerically, how are we updating our theta? So we were writing theta j is equal to theta j minus summation I is equal to 1 to n h theta xi minus yi times xji. This was the iterate which we wrote in the gradient descent. In case you have forgotten, I'll show you here. There was a alpha here, sorry. Alpha n 1 over n. Yes? Everybody okay? This we did yesterday. Comfortable with it? Now you help me find the complexity of this. I'll keep this slide open so that you don't read it from that. So what is h theta? Tell me, someone. Wake up. Now you're more sleepy. It is more in the afternoon, right? Sorry? So you write h theta first is theta naught plus theta 1 xi1. We are doing a linear regression, remember? So it has to be linear. There is no squares. It's just plus theta d x di. Correct? You recall this? Now tell me what is the complexity of finding one theta? How would you check? You're doing multiplications here. Where are this theta naught, theta 1, theta d coming? They're coming from the previous iteration, right? The previous iteration is something like which we showed in this one. You started with something like theta naught is minus 900 and theta 1 is minus 0.1 in this example. And in the next step to compute your theta, which is coming, this is line, you already know your theta naught and theta 1. That is what it means. And you already know your point. You know the ith, first dimension of the ith point and the d dimension of the ith point. So how many multiplications are you doing? D multiplications, and similarly D additions you are probably doing. So the complexity of computing h theta x is order of D. Yes or no? Subtracting yi is the complexity. What's the complexity of that? Just one. You're just doing one subtraction. This is a scalar, no? You're subtracting another scalar. You're doing one subtraction. You're multiplying xji. You're doing one more multiplication. I'm being more pedantic because of the non-CS people, because you don't do this every day. So that's why I'm doing. So you do D operations, additions, twice D in fact. You do D multiplications, D additions, you do one subtraction, you do one multiplication. Correct? But then there is a summation in front. So you do this how many times? N times. So the computing the whole thing is order of d times n or n times d, whatever you wanted to do. Correct? So this is the complexity of finding one theta. Remember, this is theta j, whether you're finding theta naught or theta 1 or theta 2, whatever. But you will do this for how many thetas? D thetas. You know, j is going from 0 to d. You're doing d plus 1 thetas, basically, right? So the overall complexity of running this algorithm is order of d square n. Everybody with me? Yes or no? Non-CS people, is it clear or confused? Clear? Okay. Last time I got a feedback saying that don't use the term CS and non-CS. We feel untouchable. Well, I use the term non-CS to emphasize those who don't have the sufficient background, and I don't miss out on you. So that's why I use it. I don't know how better to say that. Okay. So now let's go back to the complexity. So the complexity goes like this. So you need, so the cost of updating is dn, and cost of updating all theta is d square n. So which is cheaper? So if your d is nearly equal to n, in that case the numerical method would be cheaper because there is a d cube here. Correct? But if your d is much smaller than n, let's say your dimension of the data is 100, but your number of points are 100,000 or a million, then both are equally same because d cube is still very small. Is everybody okay? So, I mean, ideally you should first try the closed form solution. If you run into the problem of this matrix being not invertible, then fall back on the numerical technique, which is always work, because numerical technique has this alpha playing around. So you don't know what value of alpha to use so that you converge in a decent amount of time. Everybody comfortable? Should we start regularization? Okay. So this took away so much time. So now we come to the lecture which I had planned for today. which is regularization. I'll not open the slide. I'll just first motivate you something. Whatever I keep, the reason I write here is the based on student feedback only, that when you write, then we understand it better rather than just explain on the slide. But if this is slow for you, I can teach from slide. That's much more easier for me, in fact. And I don't have to do this extra work. But let's see. So we're talking about regularization. This term is used in many places, but we'll tell you what's the connotation in case of machine learning. Here we'll talk about specifically for regression, but it could be used for other machine learning models as well. So the very first thing which we want to know is what is bias and what is variance. So that's something we'll study. To do that, the thin book which I brought on the first lecture, do you remember that intro basic lecture to machine learning? Like I said, if you're not a CS major, buy that book. It's not too expensive. It tells these small things really well. So this, what I'm telling you, is from that. I thought he explained this really well. So what we'll do is, let's say your actual output is the bull's eye here, where you throw the darts, something like this. And the data points which you are predicting are somewhere like this. And maybe it's better to draw all of them. So what's the definition of a bias and what is the definition of a variance? So what bias means that how far are your predicted values away from the actual value. That is what is called bias. And what is variance? Variance is, it has nothing to do with the actual value. Your predicted value, how spread out they are among each other. That is what is called variance, which you find anyways, given a set of data point, find the standard deviation and variances, you find the mean, you subtract it from the mean and see how far you are away from the mean. So that is what is variance. So variance has something to do within the predicted values, and the bias is with respect to the given actual data which you're working. Okay. So if you look at, let's start from the third figure. This figure left one. So the dot in the center is your actual value. Remember the yi's in the regression which we were doing, and the crosses are the y hats. They are number of predictions you are doing here. So if you look at, are they close to this? No, this is far. So this is biased. So this is a biased set of data points. And is the variance small or less? The variance is small because with respect to each other, they are close. But with respect to this guy, this is far away. Correct? So let's redo, not make the figure dirty. Okay. If you look at this figure, the bias is also small. The variance is also small, right? So this column is low variance, because both of them are low variance. This one is high bias, and this is low bias, and this is high variance. So in this example, if you look at these data points, they are slightly spread about. So their variance is high, but I mean, maybe I could make this point slightly more closer. They are not too far from this relatively, so their bias is still low. But when you look at this figure, they are spread out and they are far from the center, so they are high bias and high variance. Everybody okay? So your goal of your machine learning model is to have a trade-off between to bring these variances and bias down. That's what your goal. But in the process, you should not forget that your main goal is to reduce your error between the actual and the predicted value. So there's three different things you have to worry about. You have to worry about the bias, you have to worry about the variance, and you have to the actual error between the actual and the predicted value. Okay. So now why are we studying this? All this is in the slide. I'm working it out because I'm trying to explain you. Hai na? So now what we want to do is, the next slide, let's say I've got this set of data points and I draw this line here to use the same set of data points, and then I draw one more set of points. This is the same set of points, but they are different curves which are going around it. Arey, what's going on? It's not liking it. Maybe I'm clicking on some key which is... Okay, let's see the slide. Okay, let's do the first two. So if you look at the stars are, in this case, I shouldn't have used stars, I'm sorry, because you will get confused. Stars are, I should have used dots. And these are also, let's say, dots. So dot, 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 and something like this. So if you look at the first figure, the dots are your actual data points. Hai? So this is your x values and this is y value. We are working in a simple, when I say, I mean one dimensional. The value of x is one dimensional. Linear, in this case, the linear regression I'm trying to do, this one. So let me not write linear here. So it's a simple one-dimensional regression here. The dimension of x is 1. Y we've always taken as 1. We have not done multivariate last time also. Hai na? We just changed to multiple with the x. So now if the dots are your actual values and this is the line which you have predicted, then is this biased? High bias, high variance, low bias, low variance, what is it? Tell me that first. Well, the bias is high because you're still far. Your line, prediction line is the straight line. You're still far from the actual point. So this is high bias. What is the variance? Variance is low, no? It's just the line. This is the predicted line. That's why I removed the crosses so that you don't get confused. If it makes you better with the previous thing, I'll put crosses on the line. So these are the predictions, the line which you have figured out by linear regression. So this has a high bias but has a low variance, right? So such cases are referred to high bias and low variance are referred to as an underfit curve. Underfit is mostly coming from the high bias. It's just that it happens to have low variance in that case. When you're actually not matching the data, that the bias is high, then you say you underfitted it. Okay. Now what I do on the contrary, I should not do this perfect fit. Let me draw this bad fit which I'm to do. So the points are still the same. This guy and this guy. And now what I do is I go, please don't get erased. But you get the point, right? So there's some curve. There's some curve which goes like this and the points are somewhere around. Maybe now it will like it. Okay. So now if you look at this, what's the dots are the Actual, and the line is the predicted. You can put crosses on the line to just remind you that the crosses are predicted. What's the bias here? There's almost no bias because it's passing through all the points. So there's this low bias or no bias. What's the variance? Variance is high, no? Look how spread out the points are because of the curve. So this is high variance. So when you, usually we mostly focus on the bias. So if you look at the low bias case or zero bias case, this is the case of an overfitted curve. So this is overfitting. This was a linear regression, but this was a non-linear regression. Why it's a non-linear regression? Because the curve is non-linear. It could be fourth order or fifth order, correct? So regression, if you do linear regression, it has a problem of underfitting now, which you have seen, because it is very rare that in real life the data would be linearly related. You know? So you would go for non-linear regression. But the problem with non-linear regression comes is that you may end up overfitting it. You may try to exactly match the data when you're trying to train it. When we say train it, you're finding this theta naught, theta 1 and so on and so forth, correct? And then when you're about testing, then you'll completely fail because you have exactly fitted the curve. Everybody with me? So that brings us to the point of the need of regularization. So what regularization says that if you have a model which you are ending up overfitting, can you do better without reducing the non-linearity? I mean, of course, in this case, if what I had done, let me see if it doesn't run away. So if I had drawn a curve like this, this would have been an ideal fit. This kind of a quadratic function. So this is linear, this could be fourth order function. This is the first order function and this is a second order or second degree function. So in this case, the bias and variance both are low, which you want to, minimize. In fact, it may not exactly pass through the point. What it could do is, it could go just around them. But that would be good enough for us because we are trying to train it. So here the bias is also low, the variance is also low, and it's an ideal fit for you, correct? So what we are trying to say here is that when you, typically you would go for non-linear regression and increase the degree of the thetas which you are trying to carry with you. But then you may end up doing overfitting. So without bringing the non-linearity down, can you do something to bring this down? So that's the goal of regularization. So let's go to the slide and then tell you. So this is what I just told in the first slide. This is what I told now in the second slide, right? This was high bias, low variance underfitting, high variance, low bias overfitted. This was a linear regression. Both of these are non-linear regression. I've just made the thetas here with a tilde so that you don't get confused. Here, remember, now what we are doing non-linear. So instead of, okay, the people at the back may not be able to see. So let me make it bigger. Okay, so this is linear, alpha, beta, which we used in the one-dimensional case, theta naught, theta 1. So instead of making this n-dimensional with theta naught, theta 1, theta 2 in the case of a simple linear regression, what we have done is we have increased the power of the x. Here, when you are doing multiple linear regression, the power of x was still 1, the dimensions of x were changing, x1 to xd. Here, the degree of x is changing. So this is a quadratic function, this is a quartic function. So here I have mentioned tildes on them so that you don't confuse with the earlier thetas. Is everybody okay? All right. So all this is written, what I'm just talking. Okay, now brings us to the motivation of regularization. So the motivation for regularization, like I said, one reason was that you are here, quartic, try to reduce the non-linearity, bring it to quadratic, but you don't know where to stop. Maybe you try at 100 and it works really well at 10. So you would not know, you will start at 5, 10, 15. How much will you experiment to get your errors down? So that's why this part of machine learning is experimental machine learning, where you don't know how to choose a model, which model will be best for you. So let's say you end up taking the worst case, highly nonlinear model, right? So in this case, let's say I took up a quartic function. So if you look at these two quartic functions, one written in green and the other written in blue, both are fourth degree or fourth order. They are quartic, QUARTIC, the quartic, the fourth degree, what we call. But they are having a very different picture. Correct? What's the difference? The constants in fronts are different, right? If you look at the first one, it's -1, 7, -5, -31, 30. These are the thetas or theta tildes. Now I'm referring to this tildes because I'm working with a non-linear context. When I divide that by a -5 value, I end up getting the second curve. 1/5, -7/5, +1, +31/1, -6/6. So if you look at the green curve, how much bias it has. Bias for both of them is low, but the green curve is probably doing much more work. The variance there is much more. But if you look at the second curve, it has a much lower variance. So it has a lower bias and a lower variance which you want to do. Correct? So the idea behind regularization is that without decreasing the non-linearity of your model, you bring these constants down so that you are able to reduce the variance in the problem which you have. Is that okay? So how can you do that? So what we'll do, we'll add artificial terms to it. So I'll just open my writing pad. I'm going very slow on this because motivation for regularization is more important. Once you get that, the algebra is very simple. It's 4 slides and you can do it because you've done that algebra before. So you had your j theta. What was our j theta? Can somebody remind me? Summation of I going from 1 to n, h theta of xi minus yi and square. Correct? This is the j theta which we had. Correct? So now I'm switching back to the case of let's say the linear regression, right? So in the case of linear regression, this was theta naught plus theta 1 xi1 all the way till theta d x di. Correct? Thetas are the one which are not known to us, theta naught to theta d. So the question, the motivation which is coming from the left part of the screen or the slide is that I want to reduce these theta, and what are we trying to do? We are trying to minimize this j theta. Correct? With respect to this. This is the optimization problem which we are trying to solve. So to get the theta values along with this to reduce, what I'll do, I'll artificially add thetas to the end. So what I could do is, here I could add summation of theta j going from 1 to d. So I add all the thetas there. So when you're trying to minimize this guy would also get minimized. Correct? That's one way of doing it. But a better way of doing it, to do it with squares. Why? Because there are two reasons. One is there is a least square here, so that there is a consistency in that. Second is you get a quadratic function which is convex, which you saw the square thing got us convexity and got us nice property. So the idea behind regularization is add these terms here with a lambda. How much of regularization you want to do. So if your lambda is really small, which term will dominate? Let's say lambda is really large, which term will dominate? If lambda is really large, then this term will dominate. And you want to minimize the thetas, and all the thetas will tend to 0 because you're squaring them. Correct? Theta naught square, theta 1 square, theta 2, except theta naught. Theta naught is we don't want to do because here the theta naught is without x. Let's say theta 1, theta 2 and so on and so forth are there. They will all tend to 0. When all of them will tend to 0, which means that it will become just a straight line, which I'll show. But if your lambda, if this is really small, then which term will dominate? the first term will dominate, which means that the thetas here will not go to 0 as much as you want. So this is controlling the amount of regularization you want to do, whether you want the thetas to go down or you don't want the thetas to go down. If I don't put a lambda, then maybe these values are always less and this will dominate, all thetas will tend to 0, and then you will just get a straight line theta naught, nothing else. Or if I make this 10 to the power 6, then this will be really small. Sorry, if I make this 10 to the power minus 6, this is really small. This term will dominate, so whatever nonlinearity and high, variance it has, it will be there. Is it making sense? So this is what is written on the next slide. So what you do is you do j theta plus you add it. So in this example, we had theta naught, theta 1, theta 2, theta 3, theta 4. So we added regularization only on theta 1 to theta 4 because theta naught is without the x, no? So there is no regularization needed for this because it is going to be fixed. And that, what I told was that if lambda is large, then this term will dominate. All the thetas when they're trying to minimize, because minimize j theta means find the minimum value, it's a square function, the minimum value it will be 0, so all the theta 1 to theta 4 will tend up to 0 and you will only have theta naught. So you will come back to the case of underfitting. So you've really underfitted. You got the nonlinearity of the function down almost to a straight line. But when lambda is really small, let's say this term was not there, then you're still overfitting. So there is a trade-off between what lambda you choose, how much of the regularization you want to add so that you bring the nonlinearity down to a place where it's low biased and low variance. So in the machine learning context, such variables are called hyperparameters. The first hyperparameter which we saw was lambda alpha. Where did alpha go? In the gradient descent case, where you control how much slow you're going. Another hyperparameter here is lambda. What are hyperparameters is that you play around with the data a little bit and figure out what's the best value. That is what is hyperparameter. That you take your input data, you first, ideally what you would do in machine learning, take the input data, train it, find all these thetas, and then have new set of data to test what the value is. Let's say I use the data, draw the regression line, and now I predict. That is training and testing. But now that you have something else playing a role, you separate your data into three parts. You can say training data, validation data, and testing data. So training data will first tell you what theta naught and theta 1 and so forth are. The validation data would be to play around and find the ideal value of the hyperparameters. Once you have that, then you end up getting testing. This concept is going to come back again and again with every model I do, but I'm just trying to give you the first primer of what we're trying to tell. So is everybody clear that why are we adding theta squares on the right side of j theta? So that we can bring the nonlinearity down by changing the theta values. Is that okay? Doubts? Yeah, please. Correct. Only for overfitting. Like I said, for underfit, when you end up with underfit, oh, we are already out of time. Sorry, I'll just finish it. So if you look at the first figure here on the left, it's underfitted because it's a linear regression, and the property of linear regression, it will be underfitted. The bias will be high, variance will be low, but you can't do much about it. The way to fix this is to increase the nonlinearity of your model. To increase the nonlinearity of your model is to find a model which has the function which has higher degrees in x's. Rather than just x's with power 1, you'll have x square or x cube and x4. When you go to higher, how much higher you want to go? So if you go to quadratic, it turns out to be a good fit, but when to the 4th degree function, it became an overfit because the variance became really large. So now to bring that down, I don't want to, and one way is you keep playing around. You go to x to the 100, to x to the 50, x to the 30, how much will you do? So rather than that, you say add this regularization term, which will naturally bring this nonlinearity down by changing the theta value, which I showed with this example. that they are both fourth order function, but in one the theta values are large, the other the theta values are really small. To get the theta values to come to really small, you add j theta with some theta values. Now the sum theta values, I am adding them as theta squares because I'm trying to minimize j theta, so I'm going to minimize the sum of theta squares as well. And I know the minimum value of theta squares will tend to 0 because it's a square function. Makes sense? Any other doubt? Yeah. More up? Huh. Here it is x square and here it's still x4. Thetas, that's what I'm saying. So let me just try to tell you again then. I think if you're getting confused, then probably I've not told you properly. Forget about this. So there was some j theta here. What's your name? Ayush. So just 1 minute, let me just re-emphasize because you're getting confused. So what Ayush is asking, that this is a fourth x to the 4 with linear thetas and you are adding theta square terms here. That is what he's asking. So let me emphasize this again. So Ayush, what I could do is, I don't know my model, so I have to use a nonlinear model. So I could end up working with x to the 100, let's say in that case. I don't know. Here I can visualize, so I know that 4 is turning out to be bad, 2 is better. But in a data where you have multiple dimensions and so many data points, you can't see anything. So you have to try it somewhere, or your end user might say, I feel it may be this much nonlinear. So you start with x to the 100. Now, you know that if you bring if x to the 100 is giving you a high, low bias, of course, high variance, you can bring that down. You can bring it to x to 50, x to something, but that's playing around. I don't want to do that. What I'm trying to tell you is that even if you stick with x to the 100 and bring the theta values down, you can still bring the variance down, which we show in this figure. If you see, both of them are x to the 4. Green curve has a high variance, overfitted. The yellow one is low variance, both have zero bias almost because they're passing through the point. This blue one has a low variance and it's not overfitting, even it's x to the 4. How did I get it? I was able to reduce the thetas, correct? Without playing around with the power or degree, I reduced the thetas. Yes or no? So how do I reduce the thetas automatically? To do that, what I'll do, if I can add this, because I'm trying to find the minimum of my residue function, if I can add here a function of theta which minimizes my theta along with the j theta, then I'm good. Correct? There are many ways of picking f theta. One reason I said I could just do theta j is j going to 1 to 1. I just add the thetas here. Simply a linear one. Theta 1 tilde plus theta 2 tilde plus theta 4 tilde. That's one way of doing it. But I don't want to go to a term where plus and minus play a role, especially when my j theta is quadratic. Another reason is that I want this term to have a 0 minima. So to get the 0 minima, what I'll do, I'll add the squares, which matches my quadratic residue, and it also ensures that the function stays convex because the quadratic functions get you convexity. Another thing it gets you is that the minima of this is 0. So when you try to reduce this, you will end up with theta tilde equal to 0 all the way theta 4 equal to 0. If let's say there was a constant 1 in front, this term will not dominate, this term will dominate, and all the thetas will 0, and only theta naught will play a role, and you'll get a line like this. But if let's say you add a slightly more constant to it, let's say 0.5. So maybe the function will start looking like this. When you make it 0, yes, it will start overfitting. Does it make sense? I have repeated the whole thing again. Is it clear, Ayush? Everybody okay? At the back, I can't see your faces, but if you have any doubt, ask me. So we'll stop here because I have overrun the time. The next task is just to add this regularization term, which I said, into both our closed form solution and the numerical solution. So the next 4 slides on that. So you add this in the closed form solution, you get a pseudo inverse. You add that in your numerical and you get a slightly different function. So these 4 slides, we'll do it on. If there is time, I'll come in the lab tomorrow and finish it so that Monday we can. So, okay, 1 minute. I'm sorry you're getting late, but there are 2 things. Monday again, I'll do extra lecture on optimization, because before I start support vector machines, you need to know a little more of optimization. Did you guys read my notes? Was the extra lecture useful? Okay. So that's one thing, which means that these 4 slides, I'll come to the 2 labs separately tomorrow and finish it. And then Monday we can start optimization extra lecture. Tuesday, Wednesday will be the support vector machine lectures. Second thing is the computer science people, tomorrow 4:30 there is an advisor meeting. You got an email, Gaurav? So, which means I'll also have to be there, which means that I'll come back at around 5. So you guys can also come. We'll do a 10-15 minute meeting. There's somebody did suicide in Kharagpur now. So you can turn this off, hai na? So which is unfortunate. This guy had